This is a recap of what I talked about on Friday in trig-precal for people who weren't there, or for people who were there and want to know more about it, or see it again. So the first thing we looked at, I'm trying to get at some issues of, now that we know some formulas for things like investments or population growth or radioactive decay, how do we work with those and how do we answer some interesting questions? And there's a couple of ones that are of connections that I didn't make before, which are really crucial. One is, there's a really nice rule we'll discover for the doubling time for an investment, and it happened to come up on career day, which was pretty cool. That synced up, but it came up with a number that I don't think is quite the best number to remember, so we're going to get a slightly different version. So here's the formula for continuous compounding. So that's one issue, is that I'm assuming the compounding is continuous, and that's really a pretty good approximation, unless even if it's like monthly compounding, it's pretty close, unless the interest rate's ridiculously high, which it's never going to be, probably. So we're going to use the continuous compounding assumption to make things simple. And we're going to ask, how long does it take to double your investment? The first thing that we've pretty much noticed already is that it doesn't matter how much you invest. It should always give you the same answer to this question for the same interest rate. It should really only depend on the interest rate. If I put $1,000 in, it should double to $2,000 in the same amount of time as my friend's $10,000 doubled to 20. And we're going to see that right away in the math. What we're going to do is we're just going to set A of t equal 2p, because that's double your investment. And we're just going to solve. So 2p is p e to the rt. The p's cancel. And we're going to assume that r is known. Let's put that up here actually. Given r, how long to double your investment? Okay, so we're assuming r is known, and we're solving for t as a function of r, in terms of r. So here's the crucial step. We need to turn that e into an ln. The way you strip off an exponent out of here is a log, and since it's a base e, we're going to use a natural log. And so we get a simple formula. ln2 over r. And ln2, if you calculate it, it's 0.6931. It's a really good number to memorize, but that's not something non-geeky people usually do. And what does that say? Well, for example, first of all, I'm just going to approximate it. We want a rule of thumb here. We don't really need something crucial. For one thing, we already assumed continuous compounding, which is probably an approximation already. So we're going to say t is approximately equal to whoa, sorry for coughing in your ear like that. That's really rude, but I still have my cold. Okay, 0.70 over r. That's pretty close to the 0.6931. And so, for example, if r equals 7%, which is really 0.07, then t is going to be approximately 0.70 over 0.07, which is 10 years. If that was an annual interest rate, let's say. So 7% per year. Okay, so the way finance people usually state this is express r just in percent. Don't convert it to its actual numerical form. And the claim is, if I divide 70 by 7, oh, I get the same answer. Okay, so the idea here is t, the doubling time, is approximately equal to 70, which is just this number times 100, over r in percent, which is the real r times 100. So you're just multiplying the top and bottom by 100 and it cancels out. So that's called the rule of 70. For some reason, on career day, the person said it was a rule of 72, and I'm not sure exactly why. Maybe he's using a different approximation or something like that, but I usually hear it as the rule of 70. Take 70 divided by the interest rate. So another example would be if r equals 3.5%, not to the fifth power, sorry, there we go, wrong key, then t is roughly going to be 70 over 3.5, which is 20 years. So a 3.5% rate is not an unreasonable investment. in most climates you can get that with a pretty conservative investment, and it'll double in 20 years. That's not so bad for just letting it sit and not having to do any work. Okay, so this idea of the ln2 over r, which is the exact formula, mathematician's kind of version, and the rough and ready finance version of the rule of 70 is really, really handy to get an idea of what things like what interest rates mean. So a very analogous thing is if we look at radioactive decay, then what we're going to do is we're going to look at half-life. Okay, so here the setup, I'll follow the book's notation. We have a mass, we have some object, some radioactive sample, and its mass is a function of time because some of it actually decays and goes away. It's an e to the minus something times t because it's going to be a decaying exponential. And then the k is called the rate constant, or the decay constant. So here, k equals rate, well, let's call it the decay constant. Okay. And we'd like to know how long, so given k, for example, how long till we have only half of the substance left. Once again, we'll discover it does not depend on how much we started with. So for m of t, I'm going to put in m sub 0 over 2, and we're going to say, okay, if I know I'm interested in the mystery time when I get half of what I started with, that's going to be m naught over 2, and I'm going to put in h for half-life. So I'm solving for the half-life. I'm going to use a special letter here, the way the book does. Okay, so the m naughts cancel right away. We get 1/2 equals e to the minus kh. We use logs to strip that off, and so we get ln of 1/2, whoops, equals minus kh, or h equals something that looks a little awkward, but I mean you could use it in this form, but we're going to discover there's a better way to do it. Minus ln 1/2 over k. And the thing is that that's equal to minus ln of 2 to the minus 1 all over k. Whoa, I don't want to highlight all that. And the minus 1, one of the rules of logs is the minus 1 can come down and cancel that guy. And we get exactly the same rule, except with different letters, as for the doubling time, which makes sense. The analog of doubling for a growth is halving for a decay. Whoops, that's a 2. There we go. And sometimes we want to solve it the other way. Suppose we know the half-life, and we'd like to know what to put in as this mystery rate constant in the exponential expression. This master formula is a really good way to express this thing, but it's a little obscure. It uses e, which is a little unfamiliar still, and this k, it's like, well, what does it mean? Well, if somebody gives you the half-life, then it's pretty simple to figure out the k that you should put in this formula to replicate that and put that into the calculator, graph it, do algebra with it, solve equations, things like that. And so this is another example where we have this ln2 over something formula. And so that's another, it's cool how it fits in with the rule of 70. And so if you understand doubling an investment, you understand half-life, and it seems like, whoa, that radioactivity, what does that have to do with money? But it's a pretty cool connection. I'll stop there and record a little bit more on a different video.